Так, значит, итого трансляция запустилась. Давайте проверим.
Да, все отлично.
Так, okay, so the broadcast is on. Anyway, ahomology theory is what is it? Let's just briefly remember what we did last time. It's a functor from from sufficiently nice spaces to Z greater to billion groups, which in most examples we'll look at will mean Z greater than or equal 0 greater to billion groups. And this functor has a few properties, one of which is homotopy invariance, and can anyone give me another property which we talked about last time? Well, yes, long exact sequences. We don't have pairs for the moment. We don't have pairs, but we will talk about those in a while. Sorry, long exact sequences for, yes, the way we define those indeed involved looking at CW pairs. Yes, but no, there is another way to include pairs. And we'll talk, which is relative homology. We'll talk about relative homology in a while. Maybe today, maybe later. Anyhow, long exact sequences. Is there anything else we talked about last time? Is this it? We did mention it, but we didn't talk about it in the detail it deserves. We'll talk about the homology of a point in a minute. But we did calculate a few examples, and those examples started by me saying, suppose the homology of a point is Z in degree 0 and 0 in all other degrees. Then the homology of something is something. Okay, so as far as I remember, but I might be wrong, we did cover these two properties or axioms. And we did calculate a few examples, and this was it. So there are two more. There are two more properties which I will now state. These are well, these are useful, but anyway, they're useful, but for example, this one in most examples follows from this one. So this property follows from this one if A has finitely many elements. Now let's look at this formula and see whether we understand what it says. What is H tilde? It's the kernel of the homology map induced by the unique map from a given space X to the one-point space. Well, what is H? The functor must have in order to be called a homology theory. Anyway, this axiom. Oh, okay. So sorry. We have explained H. We have explained H tilde. What is wedge for all A? No, sorry, for all alpha inside A. Well, it's a wedge or a bouquet of a possibly infinite family of pointer spaces. So X, alpha are pointer spaces. Okay. What is the direct sum? The direct sum is the direct sum. But this is probably clear. What is there a map from the right-hand side to the left-hand side? Yes, there is. Each individual X alpha is maps to the wedge. So we get a map from the homology of each X alpha to the homology of the wedge. And by the general nonsense, we have a map from the direct sum to the homology of the wedge. And this property says that this map from the direct sum to the homology of the wedge is an isomorphism. And as I said, if there are finitely many summons in the wedge, this is nothing new. This follows from the previous axiom. Are there any questions? Okay, so a homology theory is standard if the homology of a point is something in degree 0 and 0 in degree non-zero. And we will mostly talk about the standard homology theory, but all calculations we did last time apply, in fact, to all homology theories. So let's recall that last time we calculated the homology of what? Let's try to remember. Can anyone tell me at least one example we've already calculated?
Orientable surfaces?
Yes, we did calculate the homology of a surface which is orientable of genus G without boundary. And this calculation works equally well for an arbitrary homology theory.
Even at non-standard?
Yes, for all homology theories such as the K theory and so on. But of course, there are lots of spaces for which we can't deduce the K theory using the same trick. And the extent to which a homology theory differs from the standard homology theory is measured by the Atiyah-Hirzebruch spectral sequence, which we will probably not talk about in this class. But the thing is, for low-dimensional spaces, all differentials in the Atiyah-Hirzebruch spectral sequence vanish for dimension reasons. So we are able to get the answer which works for every homology theory, and this is not true for more general spaces. Anyhow, so we use capital H with G. So capital H of X comma G is so we use capital H of X comma G to denote the standard homology of X with coefficients in G, which means H naught of PT is G. the most important G, and we'll see why this G is most important, is G equals Z. So if we do not write a G here, we will mean that G is Z. But some of the things we'll discuss, in fact, work for an arbitrary homology theory, in which case we will use lowercase h to denote an arbitrary homology theory. Okay. Now, well, before I erase everything, I would like to say a few more things. The long exact sequences in the second property should be functorial. And this isomorphism should be a natural transformation. Well, both the left-hand side and the right-hand side are functors, and functors from the category of collections of pointed spaces to graded abelian groups. Is in fact a natural transformation, well, basically by more or less by construction. We already have this map, and from construction it follows that it's a natural transformation. So we don't have. So this is automatic, but here this is something we require. Does this make any sense? Yes or no? Yes. Okay. Anyway, are we ready to erase everything? Well, let's erase everything. And well, what do we do next? Let's see. There is one other thing which is quite useful. So let's discuss it. Let's discuss it as well. the Meyer-Vietoris long exact sequence. And after we do this, we'll do a few calculations. The sequence comes in a few versions. We'll consider a simple one, and later on we'll see other versions when we need those. Again, I'm not stating the most general version, just something which will help us to do a few calculations. Suppose we have a CW complex X, which is the union of two subcomplexes A and B. Then there are the following long exact sequences. Well, the first one let me put here plus minus, and here minus plus. Now, and by the way, let me state this thing for an arbitrary homology theory, because the proof is exactly the same, as we'll see in a minute. So we have this long exact sequence. If I put a plus here, I need to put a minus here, and vice versa. Now, does everyone have a suggestion as to what exactly this plus and minus actually mean?
Send the homology, for example, take one element in homology for A intersect with B, is sent actually plus in the first component and minus in the second component in A and B, correct?
Well, we have a map from Hn of A intersected B to Hn of A.
Yeah.
And similarly, we have, which is induced by the inclusion A intersected B in A. And similarly, we have a map from Hn of A intersected B to Hn of B. And so we can take the direct sum of the two maps. And what we get is a map from Hn of A intersected B to this direct sum. Similarly, we have maps from both summons to A union B. But this time, if we took a sum here, we need to take a minus here, and vice versa. Does this make sense? Окей. Значит, у нас есть отображения отсюда сюда, отсюда сюда. Какие? Индуцированные вложениями. И, значит, у нас есть отображение отсюда сюда и отсюда туда же. Тоже индуцированные вложениями. И вот здесь мы берем сумму отображения индуцированных вложениями, а вот здесь мы берем разность.
В смысле, как отображение равно углу?
Да. А можем взять наоборот, можем взять здесь разность и здесь сумму. Значит, там большой разницы нет. Does this make sense? Okay. Now, how to prove this? Oh, by the way, I said sequence is. Where is another one? Well, I can take the same one with the tildes and I get another exact sequence, and this is it. And the sequence of these with respect to maps of ordered CW triples X, A, B, such that X is the union of A and B. The word ordered is important because at some point we take a plus, and at the other place we take a minus. So, in particular, we can't swap A and B. Well, we can, but then we need to pay attention to extra signs which will appear. Okay. Does everyone understand what this what this sequence is?
Why do we have like plus and minus signs here? Like it's just in maps.
Yes. We have the maps from here to both summons here, induced by the inclusion. By the inclusions, there are two inclusions. Similarly, we have the maps from both summons to this group, which are also induced by the inclusions. And so altogether we have 4 maps. And to define this one, we take the sum, and to define this one, we take the difference. Or we could do this the other way around. We could take the difference here and the sum here.
Why do we have two maps? Like, why do we have two inclusions, two different inclusions?
Well, because A intersected B is included in A and in B.
Oh, okay, I see.
Those are two different maps. We take the sum once and the difference the other time. And it doesn't matter as long as we pay attention.
Why we use a smaller h?
Well, because this thing works for an arbitrary homology theory. It works for the standard one, but it works for an arbitrary homology theory as well. Small h denotes an arbitrary homology theory, which may or may not be standard. Are there any more questions, remarks? How to prove this? Well, are there any ideas?
You can consider a long exact sequence for a pair A intersected B and the point X.
Yes. So the one of the ways to prove this to prove the statement is to build a single exact sequence out of two exact sequences. Okay, suppose I have A intersected B. Inside A, from what we did last week, we have this long exact sequence. Where here I need to take A and collapse A intersected B. Why did I write it in this way? Because, by the way, here I also take A and collapse A intersected B. Why did I write it as a ramp? Well, because I have another long exact sequence which involves these groups, which is what do I need to take? I need to take B. Okay, so I have two exact sequences for the two couples. The first one is A intersected B, comma A, or rather the other way around, A comma A intersected B, and this is one couple, and the other one is A union B, comma B. So there are two couples, and well, we have A by A union B is the same space. Well, at least in the CW case, as A union B by B. And we have two long exact sequences which such that each third group in both exact sequences is the same. So we write it once. And basically, this is it. We can use, and yes, both rows, both the top row and the bottom row are exact, and this is it. We can use this diagram to define all maps in this sequence. Basically, we have them. We have the map from the easy ones are already clear from the definition. What about this one? Okay. I'm sorry, what's your name?
Hi.
No, Мария, я сейчас хочу что-то написать вот здесь вместо троеточия, чтобы не переписывать диаграмму. Не могли бы вы ее продемонстрировать на камеру? Значит, я хочу сейчас написать что-то в запретном месте. Okay. I don't want to redraw the whole diagram, so I will write something here, and this something is h at -1 of A intersected B. So this map is the composition of of these two. We have a map from here to here. We compose it from here to here, with a map from here to here, and we get this map. Does this make sense? Now, exercise prove that the resulting thing is exact.
Is there like some lemma that if we have some exit sequence, then if we consider like if we replace two consecutive errors with their composition, then the resulting sequence will also be exact? Can we just like
well, if we there is one thing that one needs to pay attention to. If we compose two arrows in an exact sequence, we get 0, just by the definition of an exact sequence.
Yeah, right.
But here we take one arrow from one exact sequence and compose it with the next arrow from the different exact sequence.
Yeah, that makes sense, and then we have to prove that we...
Yes, and that's, well, it's an easy exercise in what people call diagram chasing, which proves that the resulting sequence is in fact exact. And it's one of those things which are well, quite straightforward to prove on your own, and very difficult to understand if you're reading someone else's proof. So I will not even try to do this exercise now, but I suggest everyone gives it a go at home. В общем, значит, все рассуждения, связанные с диаграммным поиском, значит, невозможно понять никак, кроме как проделав их самостоятельно. Потому что если кто-то другой начинает там писать что-то со своими обозначениями, это все выглядит ужасно. И вот если вы напишете это с вашими обозначениями, пытаетесь кому-то объяснить, это тоже не подействует. В общем, предлагаю проверить вот то, что получилось в точной последовательности. But before I erase everything, does the construction of the sequence of the sequence make any sense?
Actually, I wanted to ask why there is an optional tilde.
Yes. So these tilde, the ones in the middle, are not negotiable. They need to be the tildes. But the ones over the remaining groups, they are optional. Meaning, if we include them, we get the Maya-Vietore sequence with the tildes, and if we don't, then we get the Maya-Vietore sequence without the tildes.
Is there some kind of like contraction homology, or how do they call it?
Well, it's called reduced homology.
Oh, reduced, right? Okay, sure.
So there are two versions, and well, sometimes we will want to use one, and sometimes we will want to use the other.
Yeah.
Well, okay. Now, well, let's see an application. Okay, are we ready to erase everything?
Actually, why did we have like non-optional tildes?
Well, because we haven't done relative homology yet. So instead of taking the relative homology in the middle, I need to take the reduced homology of the quotient.
Okay.
Well, let's see. What did we do? What did we do last time? We didn't yet calculate the. Did we or did we not calculate the homology of or the reduced homology of a sphere?
We just stated the result.
We just stated the result. Okay. Actually, the. Okay, let's talk about spheres. It would be logical to talk about spheres first, because spheres are, in a sense, quite simple as far as homology is concerned. But before. Before we do that, let's do an example on Maya Vittoris, since we've just discussed the Maya Vittoris sequence. Let's calculate the homology of CPN. And more precisely, let's prove by induction that the homology of CPN is Z in all even degrees from 0 to 2n, and 0 in all odd degrees. Does everyone understand what this thing means?
Do you mean the right-hand side of the equation?
Yes.
Like an array of homology?
Well, homology is a graded abelian group. Now we denote a graded abelian group by listing the non-zero components between the square brackets. It's just a notation.
Yeah, I mean, are there like zeros in here also? Or?
Yes.
Okay.
There are all odd groups are 0, and all even ones from degree 0 to up to n are Z.
So you just write in the row like consecutive homology.
Yes. Yes. The non-zero ones.
But you also write here the 0 ones.
Yes, and eventually some of the 0 ones, because because they're between.
You mean like that homology groups greater than 2 times n are all zeros. So
yes, and so we don't write them, and the ones in negative degrees are also 0, and we don't write them either.
Okay.
Okay, so how to prove this? Well, let's see. Well, for CP0, we sort of already know the answer. CP0 is a point. And then we, what do? We okay, let me take CPN and And basically, said theoretically, CPN is, but said theoretically, not topologically, this is very important. CPN is Cn disjoint union with the hyperplane at infinity, which is CPN minus 1. Okay, so if CPN is the set of all the set of all points with homogeneous coordinates x naught, etc., xn, then Cn then Cn is the subset such that the first homogeneous coordinate is non-zero. Well, if it's non-zero, by multiplying or dividing by this coordinate, we get 1 at the first place, and then all other coordinates are uniquely determined. So this thing is in fact Cn, and likewise, if we set x naught to be 0, we get another CP, CP something, but the something is n minus 1.
But doesn't it work like also topologically, but you just have to specify how those two bases are grouped together or something?
Well, topologically, no, because as we will see, the homology of the left-hand side and the right-hand side as topological spaces are the homology groups are not the same. But we will use this to get a topological decomposition. Oh, sorry, dn. What is dn? Dn is the unit disk inside Cn. Sorry, d2n is the unit disk inside Cn. And then we take the what do we take? We take the open, so this is the closed unit disk, and this is the open unit disk. We subtract the open unit disk, and this is the other space. So. Sorry, say again?
Yeah.
No. This is a union. Yeah. It's not a wedge. It's not a disjoint union. It's just a union.
How can we see the inequality points?
We take something, we subtract not quite the same thing. We subtract the interior. But every every point in CPN is either inside the unit disk in the closed unit disk in CN, or it's outside the closed unit disk. But if it's outside the closed unit disk, it's definitely outside the open unit disk. Now, what's the intersection? So let's call this A, and let's call this B. What's the intersection? Well, the intersection is the boundary to n minus 1. Well, now we have all ingredients. Let's start by okay, so here, please note, we take differentials in the Atiyah-Hirzebruch spectral sequence aren't necessarily 0. So we don't make any claims about generalized homology of CPN, just a standard one. Okay.
Why can't we make claims about the general homology theory?
Well, we'll see. In a minute, we'll see.
Okay.
Okay, well, let's check what happens with in degree 0. In degree 0, basically nothing happens. What do we have? We have Z, Z plus Z, and Z. And here we have 0, 0, 0.
That doesn't look like Myers-Briggs sequence.
Well, let's see. We have the intersection, the direct sum, the union.
Yeah, I mean, why did you write here CP n-1 if we have some different space as our B?
Let's see. Oh, yes. I forgot to say one thing. This B is in fact homotypic equivalent to Cp n minus 1. Let's see why. Let me draw a picture. To prove that these two spaces are homotopy equivalent, I construct a deformation retraction from B to C B n minus 1. How? Well, I take a point in Cn minus the unit disk. And then, well, since this point is outside the union disk, it's not the origin. So there is a well-defined line through the origin and x.
What is x?
X is a point inside Cn minus the unit disk.
Непонятно. В определении V там ЦП лambda минус откуда есть.
Да.
Вы сейчас рисуете, похоже, что это С лambda, нет?
Ну да, значит, я хочу построить для начала ретракцию из вот этого вот на Cpn-1. Но на самой бесконечности ретракцию мне строить не нужно, она там тождественна. Значит, у нас есть Cpn, значит, минус единичный диск. So we have Cpn minus the open unit disk. And we want to construct a deformation retraction of this thing onto the hyperplane at infinity. Each element of the hyperplane at infinity goes to itself. So we only need to define this R for x inside Cn, but outside the unit disk.
That's using that disjoint union from before.
Say again?
We're using that disjoint union from before. That's
Well, yes. So this Cpn is the same space I want to deformation retract B onto. And so I construct a map. What does this map do? It takes it's a deformation retraction. So it takes every point of Cpn-1 to itself. That's what deformation retractions do. What about the rest? Well, suppose I have an x in Cn minus the union disk. There is a line through the origin and x. Why is there? Well, because x is not the origin. Now this line gives me a well-defined element of C, B, n minus 1. Does this make sense?
Kind of makes sense.
I have another idea that I say it's not this. So,
Say again?
I have another idea to make this interpretation. So, the open disk is obviously homomorphic to the two-dimensional R Avant space, which is just here.
Okay.
So excluding the open disk is just like exactly the same as excluding the affine CN space.
One needs to be careful. If two things are homeomorphic, then subtracting those things does not necessarily result in homomorphic spaces. For example, every knot in the three-sphere is homomorphic to the circle, but there are different knots. You're welcome. But in this case, it's it's pretty straightforward. By the way, how to write a formula for R of x? Let's write a formula. So I have an x, which is an element of CPN minus the open unit disk. X1, Xn. But it cannot happen that all the coordinates x1, etc., xn are all 0.
Yeah.
So these are not all 0. So we take R of x equal x1, etc., xn. Why aren't they all 0? If they are all 0, then we end up with the origin in Cn.
And we excluded that origin.
Yes. And the origin does not belong to B. Does this make sense? Exercise prove that R, if we take the inclusion and then apply R, if we take the inclusion and then apply R, we get the identity map, which is clear. But if we first apply R and then take the inclusion, we get a map which is homotopic to the identity. So this R is homotopic to the identity map of B, where B is this space.
What map? Which maps x to?
Yes, R of x.
From CPN maps to CPN minus 1, right?
Well,
I mean, yeah, it is defined on CPN actually.
No.
It is not defined on CPN. It's defined on CPN minus that point.
yes, it's defined everywhere except at the origin.
Can I say that if we remove a point from CPN, then we will get something homotopically equivalent to CPN minus 1?
Yes, which is basically what we prove here.
Yeah.
Okay, does this make sense? So my claim is the map R is homotopic to the identity of B, which is pretty straightforward.
How do we prove that it's?
Well,
I mean,
think about this.
oh, okay.
And let's look at the the Mayer-Vittore sequence. Well, the first bit of the sequence doesn't tell us much. It tells us basically that H naught is Z, but we know this already. Now, the next row, the first one, is 0, 0, 0. Oh, by the way, no, it gives us something new. It tells us that H1 is 0. Why is it 0? Because we have a 0 on the one side, namely here, H1 plus H1, and we also have this arrow, which is 0. Why is it 0? Well, it is 0 because this map from Z to Z plus Z is injective.
Why is it
it's injective because both these groups. Well, let's look at this one for just for the sake of definiteness. The Z, this one Z, this Z is generated by every point. It doesn't matter which point we choose. If we take a point inside D, the inclusion of the point in D induces an isomorphism of H naught. And the same is true for the sphere. Well, the dimension is greater than or equal 1, so we know that the sphere is at least path connected. So so at the level of H naught, this map is an isomorphism. So basically the
Можно еще раз, почему там было изофиль?
какой is?
The second one.
The second one. Well, we know that we know that we know that the sphere is path connected. We know that the sphere S2n-1 is path connected. Значит, сфера линейно связана. So the group H naught is Z, and every point is a retract of. If we have a point inside a sphere, this point is a retract of the sphere. What does this mean? This means that this H naught is Z plus this H naught. But this means that this is an isomorphism between this and this. Why? Well, because Z cannot be a direct sum of Z and something else.
But the point isn't homotopically equivalent to the sphere, then how point can we retract?
It's a retract. It's not a deformation retract. It's just a retract.
Oh,
Okay.
okay.
Does this make any sense? Все, значит, имеет ли хоть малейший смысл то, что происходит в нулевой строке? What's important is, regardless of what this group is, here we have an injective map, because basically all this is Z, this is Z, this is Z. All three groups involved in this bit of the sequence are Zs, but the maps from here to here and from here to here are all isomorphisms, which means this map is definitely injective, and so we get 0, 0 here, and so this group is 0. Okay, we have two options. Option 1 would be to leave the rest as an exercise. Option 2, if we could do the rest after the break if people want me to. Let's see. Or somebody could do this even better. Somebody could do this at the blackboard. Okay, so after the break, we'll either stop here, or somebody will do the rest of this calculation at the blackboard. Okay, we need to have a break now. Are there any questions?
Could you please say one more time about injection?
Well, let's take these are isomorphisms. So this map is injective, and in fact also an isomorphism.
Okay. Would you have any example problems which are similar to the ones which will be given on the final exam, so that we can train on them?
Yes, I will probably post a few problems in next week or this week later.
Yeah, it's just important that we have kind of
understanding
what will be required of us in the end of the course.
Yes, I will post some problems.
Okay, yes, thanks.
Are there any more questions? Okay, let's have a break, and then we'll... I think it's on now. Test, 1, 2, 3. 1, 2, 3. Okay, well, let's see. Let's first of all, let's see what we have here. Well, we sort of understand what happens in this row, so let's look at this one. does this row make any sense?
I know what's written here. I have no idea what it should mean.
Okay, well, so h1 of the disk is 0. This we know.
Okay, yeah.
The disk is homotopy equivalent to a point. h1 of Cpn minus 1 is also 0. We know this by induction.
Ah, okay.
h1 of the sphere, well, by the way, this h1 of the sphere is not necessarily 0, but it is 0 if n is greater than if n is greater than 1. Well, let's assume for a moment that n is greater than 1. So then we have 0, 0, 0, everything is 0.
Okay.
But what about this one? Why is this group then 0? Well, on the right we have 0, and on the left, well, on the left we have something. It's not 0, but the map here is 0. Why is it 0? Because the one that comes after it is injective. The kernel is the image, the kernel is 0, so the image is 0, so the map is 0. So we have this unknown group, and on the right and on the left we have 0. So this group is in fact 0.
Okay.
Okay, well, let's use this board. So let's continue this this exact sequence. So we've calculated h1 of Cpn. Let's calculate h2. Да, мы пытаемся посчитать когомологию CPN с помощью Майера-Виториса. So we have, yes. Okay, so we have calculated the 0th row, the first row, and we want to calculate the second row.
So by induction we know this is 1, right? Or sufficiently large.
Okay, so well, first of all, let's let's start with this group. This one is 0 if n is greater than 1.
This one is z if n is greater than 1, I think.
And this one is z. That's right. If n is again greater than 1, if n is 2, for example, we have CP1, and we suppose by induction that we know that this is z, and this is 0.
Mm-hmm.
Okay, so we have 0 something, which we don't know yet, and then z plus 0, and then what is this group? Again, assuming n greater than 1.
N greater than 1, this is greater than...
And 2n minus 1 is also greater than 1,
mm-hmm.
and in fact greater than or equal 3.
So that would be also 0.
So yes, so here we have 0. So we have 0, z, something, 0. which means we have 0 here, 0 here. So this map is an isomorphism, and we have calculated the second group. Okay, so we've calculated the second group, and then it goes on and on until we get to. Please be careful. No, don't give me the chalk yet, but please mind the step. So we continue in more or less the same manner before we get to degree close to 2n. Okay, let's write the long exact sequence in degrees 2n minus 1 and 2n.
Okay. So the whole.
Well, yes. Let's write all terms for 2n minus 1 and also all terms for 2n. Okay.
So we know
to the homology.
Don't erase it for just a bit.
Okay. Okay.
Okay, I hope the code for enough time for someone to propose and look at it now. So, yeah.
Okay. So let's erase everything, and let me state just one thing which is useful. And we sort of saw this in the example we've just considered. Well, suppose all spaces A, B, and the intersection are path connected. Then the Meyer-Vittori sequence for any standard homology theory actually starts in degree 1, not in degree 0. What on earth does this mean? Well, this means the initial part of the sequence is and the map from this G to G plus G is injective. So, since this map is injective, here we have 0. And here we have G. Actually, if A, B, and A intersected B are all path connected, just for stupid reasons, the union A union B is also path connected. Just take one point in A, one point in B. We can join them both to some point inside the intersection. So we already know that this group is G. But even if we didn't know that, we would be able to deduce it by using the Meyer-Vittori's exact sequence. But the point is, the first part of the sequence can be dropped. Why? Well, this map is injective, so the map on the right is 0. And so the interesting part of the sequence begins at H1. Does this make sense? This sometimes helps. Имеет ли смысл, что только что произошло?
Это только для линейно связанных?
Только для линейно связанных, да, конечно. Ну, потому что иначе вот это отображение для нелинейно связанных совершенно не обязано быть инъекцией. But not in general. So exercise take A take A union B to be the circle, S1. Take A to be the left half circle and B to be the right half circle, as shown in this picture.
Closed house, right?
Yes. And the exercise is to calculate the Meyer-Vitoris sequence for this example. And in this example, this map is not injective. Okay.
What's the word in the bracket there after the group 1?
Instead of. So, well, the interesting part, which means that the interesting part of the sequence starts in degree 1.
Is it the exercise we are doing now? Is this exercise what we're doing now?
No. Well, I think this exercise can be safely left to people to do on their own in their spare time. By the way, it's an easy exercise. Okay, does everyone agree with what it says here? Comments, remarks, criticism? Okay, now let's move on to the next thing, which I sort of should have talked about earlier, but better late than never. The suspension isomorphism. Again, I do not state the most general version. I just state the version for CW complexes, but this is enough for most applications. So suppose I have a CW complex, then so is the cone. There is a small problem here. Let me try to remember whether or not this problem actually happens. Okay. In general, I'm not sure this is relevant to this example, but in general, the product of two CW complexes may not be a CW complex. In which case, we take we take the product topology, and then we take the compactly generated topology induced by the product topology. Do these words make any sense whatsoever? But I don't quite remember. Maybe if we take a CW complex and times it with a finite complex, the result will automatically be a CW complex. Don't remember. Anyway, the cone. The cone over X is also a CW complex, and just by looking at the long exact sequence of, and the cone is contractible, meaning the cone is homotopy equivalent to a point. Now, by looking at the long exact sequence of the couple CXX, we get isomorphisms between hn of x and hn plus 1 of sigma x, where sigma x is the cone of x with x collapsed. Does this make sense? Well, if it so happens that this thing is not a CW complex, which I'm not sure is actually something we need to worry about. But even if it is this is not a CW complex with the product topology, we can always take the compactly generated topology by the product topology and get a genuine CW complex.
So what did you write there with compactly generated topology?
Yes. If the product topology already is compactly generated, then we don't need to do anything. And if it isn't, then we take the compactly generated version. Значит, бывает так, что произведение, то есть топология произведения, значит, вот в обычном смысле топология произведения, содержит слишком мало открытых множеств. И тогда нужно взять компактно порожденную топологию произведения. Но для практических целей это все не очень важно. Но нужно иметь в виду, что бывают сюрпризы. Okay, so we have this isomorphism, which is the suspension isomorphism, and this isomorphism works for an arbitrary homology theory. Okay, what next? Well, let's use this isomorphism to calculate the homology of the sphere. Well, the sphere the n-sphere is the n-fold suspension of the zero sphere. So we will know the homology of the n-sphere if we know the homology of the zero sphere. But what is the zero sphere? Zero sphere is just so we get these isomorphisms. The homology of Sn is basically the same as the homology of the reduced homology of Sn is the same as the reduced homology of S naught up to shift, and this is the same as the non-reduced homology of a point.
Why is it difficult to use cohomology one?
Okay, so this has yes, we'll come to this in a second. But does this isomorphism make sense to everyone? Which, well, basically we just use the suspension in this particular case. What about this one? Well, does anyone have an explanation? Let's think.
For the tilde, you just need to remove a point to be the ordinary homology sphere.
What's the question?
Well, the question is, why do we have this this isomorphism? No, this isomorphism.
We have tilt on right.
Okay, well, let's look at this group. This group is so H tilde of a two-point set is by definition the kernel of H is the kernel of this map, and what is this kernel? Well, I have a map from this group to this group, which is induced by taking the element, the unique element of the one-point set to, for example, 1. And this gives me what? This well, this gives me a way to represent this group as a direct sum of two copies of the homology of a point. Let's well, let's
Do we know anything about the homology of a disjoint union?
well, the homology of a disjoint union is the direct sum of the homology, the non-reduced homology of a disjoint union is the direct sum of the homology of the summons of the spaces that would take disjoint union of Y. Let's think. So suppose we want to calculate the homology of a disjoint union. So my claim is and this time I take the non-reduced version. Why is that?
We're talking disjoint in the topological sense, right?
Yes. This time we take the topological disjoint union. there's But we know something about wedges. So is this a wedge of anything? It isn't. Well, in general. But to begin with, let's prove another formula. Let's prove this formula. Now, and by the way, this formula or basically already implies the formula, well, this formula that we're after.
What is
So x is a C-double complex. What is x plus? X plus is x disjoint union with a point which lives far, far away.
No, we only have the previous one, right?
Then if we have this formula, then we are able to deduce this one. Why? Well, because x disjoint union y plus is the same as x plus wedge y plus, where we use the point that lives far away to take as base point, both for x and y.
So why is this?
So if we take a one point space as x, we get this formula. So why do we have this formula? Let's think.
Maybe we could write the log sequence full equator.
Yes, we can write some long exact sequence. Let's well, it's we're actually okay. So let's do it this way. Hn of pt, Hn of x plus let's try to remember what we did last time. Oh, sorry. Do I need this one? No, I need the kernel. I need somehow the kernel of the map from this one to. Sorry, no. Okay. I need an exact sequence which involves Hn. Of x plus the chain of pt Hn of x. I need to get this one. If I want to apply this formula, I need to have a sequence like this, and also I need it to split. Well, let's have a look. Well, we do have something like this, namely Hn tilde of x plus quotiented by x. Now, what is x plus quotiented by x? So we basically come back to the question we started with, how to calculate the homology of S naught. But by the way, the
why x plus quotient x has 2 points and it should contain 1 point only, right?
At 1 point.
Well, we have 1 point coming from infinity, and the other coming from x.
Okay.
Okay, so we come back to the same question we started with, namely, why is the homology of a 2-point space the same as the homology of the reduced homology of a 2-point space is the same as the homology of a point? Well, let's. So we need to somehow prove this directly.
Yeah, but we can write down this.
Say again?
Sorry.
Okay. Well. I don't know. Well, let's think for a minute, but not more. And if I can't figure it out, this will be an exercise. Say again?
The question we are thinking about now is the reduced homology on the 2 points.
Yes, the reduced homology of, we want to prove that the reduced homology of a 2-point space is the same as the non-reduced homology of a 1-point space. And if we're able to do this, we have this isomorphism for arbitrary x and y, C-doubly complexes, and we also have this this isomorphism. Okay, well. Well, we have this exact sequence.
Why is it exact?
Well, let's see where this whole thing comes from.
I guess we can use that the quotient by an empty space is the x plus.
Well, yes, good idea. So, the quotient by an empty space is x plus, and how does this help? How does this help?
If the homology of the empty space is 0, is it?
Yes, but then we want to prove that the homology of an empty zero. Yes. Well, it's a terminal object of what?
Oh, wait, so empty space should be. Wait, is an empty space?
No. The 1-point space is terminal, and the empty space is initial.
Initial, right? Thank you. So the homology of the empty space should also be an initial object, shouldn't it? Because of integrality.
It's not. Functors do not necessarily preserve limits or colimits, and the initial object is what? Is it a limit or a colimit?
Well, not this, right? This thing preserves except sequence.
So on the level of complexes, but we haven't done complexes yet. But when we do, it will be more or less clear that on the level of complexes, the singular chain complex preserves colimits. But not on the level of cohomology. And anyway, it's not automatic. Значит, да, пустое множество, начальный объект. Вот, значит, спрашивается, и, значит, одноточное множество – это конечный объект, как в топологических пространствах, так и во множествах. Вот, значит, спрашивается, значит, а что из этого предела, что копредел? И, значит, предел копредел чего? Ну, в любом случае, предел копредел пустой диаграммы, потому что значит, ничего другого здесь значит, взять нельзя. Вот, значит, ну, начальный объект, такой объект, из которого существует, значит, ровно одна стрелка. Поэтому это копредел пустой диаграммы. Значит, конечный объект, он, соответственно, предел пустой диаграммы. Вот, но функторы вообще говоря, не всегда сохраняют пределы копредела, и поэтому, значит, просто так тут ничего. В общем, да. So my suggestion is let's assume this formula and think about how to prove this from what we already know. Let's assume this formula and basically move on to something more interesting. And so the formula. So the formula, which is, let me raise the last one. Okay, so this, let me just write the following thing. So this thing is the same as Hn of Pt. So exercise. Prove that we have this isomorphism, and then we have this isomorphism for all for every CW complex X, and we also have this isomorphism again for all xy inside CW. So we have all those wonderful things. If only we're able to prove that the reduced homology of a two-point space is the same as the non-reduced homology of a point. This is left as an exercise. If people want to see this in more detail, we'll talk about it next time. Okay, let's see. Are there any questions, remarks, comments, criticism? Okay. let's let's also assume for a minute that the map from the zero sphere to itself, which interchanges the points, 1 goes to -1, -1 goes to 1, induces -1 in the reduced homology. Let's call this map, how do we call it? Let's call this map epsilon. Now, what is the n-fold suspension of epsilon? It's a reflection in a hyperplane. Epsilon. So the n-fold suspension also induces -1 in reduced homology. So we've calculated the map induced the map of the reduced homology of Sn induced by reflection in a hyperplane. Well, here is an application. Here is an application. Let me take the antipodal map. F of x goes to -x. And this map induces -1 to which power? In reduced homology.
To what sense? In what sense to which power?
Okay, so we want to calculate the map of the reduced homology of Sn induced by this. And my claim is this map induces multiplication by -1 to some power. And which power? Значит, мы хотим посчитать отображение, которое индуцирует в приведенных гомологиях антиподальное отображение сферы. В любых приведенных гомологиях там, значит, там в любых смыслах в произвольной теории может быть стандартный, может быть нестандартный, может какой угодно. Что получается?
Вообще связывать конкретно отображение на пространстве с отображением гомологии?
Ну, функционально. Вот, значит, мы сейчас ну, значит, пробуем значит, действовать из соображений функциональности. Вот мы поняли, как это работает для отражения относительно гиперплоскости. Отражение относительно гиперплоскости индуцирует -1 в приведенных гомологиях. Вот. Значит, теперь возникает вопрос, а как из этого вывести для вот такого отображения? So, for a single reflection in a hyperplane, the induced map is multiplication by -1.
Центральная симметрия — это вроде как симметрия относительно плоскости. Просто это координатный
Okay, so Maria is saying that we have here -1 to the n. Does everyone agree?
And +1 maybe.
And what's your name?
Way.
Wei?
Way.
Okay, Wei says it's n+1. So which of the two answers is correct?
Wade's right.
Yeah,
Because-
+1.
Yeah, it's n+1 because the n-dimensional sphere lives in the n+1 dimensional space, so we have to switch the sign of n+1 coordinates, not that, as I mistakenly said at first.
Okay, so using just functoriality, we deduce that this map induces multiplication by by -1 to the n+1. Okay, well, we started a bit late, we could, if this is all right with everyone, we could do one more example, or we could stop now.
We still have like 9 minutes until the official end of the class, so...
Окей, сейчас, значит, что такое official?
Ну, в смысле, в расписании написано, что пара заканчивается в 19:30.
Пора закончить. Okay, very well. So we do have time for one more example. So we have calculated the induced homology map for the map for the reflection in a hyperplane, and also for the antipodal map of the sphere. So let's do one more example. Let's calculate the induced map, the map induced by raising a complex number to the nth power. This time we're not able to say that this is the suspension of anything, because S node only has 2 points.
Yeah, we are just changing the angle of points. So
Angle.
yeah, I mean, if a point is on the circle, then it's making some angle with the center, and then if I multiply, I mean, we are raising a power, z is going to z to the power n, so the angle is changing.
Yes. Okay. Well, let's see what this map does. Well, let's first assume that n is greater than 0, because if n is 0, we have a constant map which induces 0 in reduced homology, and if n is less than 0, we could use what we already know. And the fact that for n equal -1 we get complex conjugation, and this is the same as reflection in a hyperplane.
Wait, you said we get 0 when it's the identity map?
Yes, so if n is 0, the map is constant. And this means it factorizes through the map from S1 to a single point, and the reduced homology of a point is 0, because well, more or less by definition. My claim is if n is greater than 0, then the map is multiplication by n. Well, in fact, the same applies to n negative and. Yes, the reduced homology of this wedge is the sum. So we have the following thing. We have this circle, which first goes to the wedge, and then goes to and then the wedge goes to S1 again. Now let's see what happens on the level of homology. We have the homology of the wedge. Which is a direct sum, and so on and so forth. But I need to specify if I want to relate this circle to these circles, I need to specify the map. It doesn't suffice just to say that all these are abstract circles. I need to specify the map. So I choose an orientation, and I know that this map, and in fact, well, the composition is orientation preserving as a map from the circle to itself. This we know. So I choose orientations in all circles such that all maps preserve the orientations. So we choose the orientations so that all maps preserve the orientations. Okay, now. Now the homology of the wedge is the direct sum let me use k here, and then I will use ik. Now, what is ik? Ik is the orientation preserving map from S1 from S1 to the wedge, as and this map identifies S1 with the ith factor, ith summoned as in an orientation preserving way. So we have this Hn of the wedge is this. Yes.
What does the sum mean? So what is IK with the star?
Ik is a map from S1 to the wedge, and then we have the induced homology map, which we denote Ik lower star.
So that's like homology equals to sum of maps.
Well, yes, thanks. Indeed, what I wrote doesn't make sense. Is this any better? Masha, is this any better? Okay. So we have this decomposition, and then we want to calculate these two maps in terms of this decomposition. And my claim is, well, let me call this, I don't know, alpha. Let me call this beta.
Wait, could you explain again what does IK actually do?
IK identifies S1 with our given orientation with the kth summand of the wedge. Again, so that the orientations are the same. Oh, by the way, here I have the identity, and this is isomorphic to and this is okay. So this thing is isomorphic to a sum of k copies of the homology of S1, and in such a way that the map from one copy to the sum becomes the diagonal embedding. Так, значит, имеет ли какой-нибудь смысл происходящее, или все уже, значит, нужно закругляться хорошо понемножку? Хорошо. Okay, let me just finish the answer, and I will Okay, the answer is we can identify this the homology of this thing with the sum of n copies of the homology of the circle in such a way that the first map becomes the diagonal embedding, and the second map becomes the identity on each summand. And I don't like this explanation, but I can't think of a better one.
Why is it diagonal embedding?
Say again?
Why is the map from the homology of one sphere to the homology of wedge a diagonal embedding?
Well, because let's see what happens. It's a very good question. Let's see what happens when we apply first this map and then take the projection to one of the summands. What happens on the level of circles? On the level of circles, the following thing happens. We take this circle to one of these circles in the following manner. The circles in the wedge correspond to segments of this S1. And so the map from this circle to this circle collapses everything outside a segment, and then it spreads the segment over the circle. This map is if we identify the circles in an orientation preserving way, this map becomes the homotopic to the identity. It's a key point. Does everyone understand it? No. Okay, so we have two circles. First this circle here.
Yeah, this one we are taking a map from this one to which product of this one.
And then we have a summand of the wedge. Let's identify them in an orientation preserving way. So they become the same circle. And then we have a map which is as follows. First we go to the wedge, and then we collapse everything except the ith summand.
Okay.
What is this? What does this map do? It takes the circle, collapses everything apart from a single part of the circle, and then it makes one of these circles out of this segment.
Okay, so it is creating another circle from that segment.
Yes. And so and the same thing happens with all circles. So if we identify all circles with some standard S1 in an orientation preserving way, then this thing will be just the diagonal embedding, because we identify all copies both here and here with the homology of some standard copy of S1. Okay, now we look at this map. Well, for similar reasons, the map from this direct sum to the homology of S1 is basically the identity map on each summand. So what does this map do? It takes a sequence of elements of h tilde s1 and takes the sequence to the sum. And then the composite multiplies everything by n. Does this make sense? Okay, well, I think we need to finish, and but before we do, are there any questions? No questions. Everyone's too tired to ask questions. Okay, well, let's stop, and then we'll continue next time.